presenting a brief introduction on what we call summary statistics using R. So this is just a disclaimer side. In R and biostatistics, what we're going to go through is some ways you can visualize your data properly to make sure everything is working very well. To make sure everything is working visual. Let me back up. It is a visual representation. To make sure the representation is accurate, you need to do something what we call quality check your data to make sure the figures you are drawing is correct. I will go over this later on, but this is just an example of a box plot that we normally use that can be used to create an R. So generally, statistics is a way of learning from data. You can get inferences and be able to extrapolate from your sample data to population analysis. It's concerned with all different kinds of study designs, data collection, requires judgment, as we will see later. And the biostatistics is a statistics applied to biological and health problems. Specifically, when you're doing a research design, actually a research study, you have to ask yourself some questions. The what, the how, sample collection, data collection, what should be collected, and the analysis is just as important as data collection. You have to analyze it properly so your audience will be able to understand it. You can also conclude from the data based on the analysis. Now, R, it's operated from what they call a crane mirror. Crane mirror stands for Comprehensive R Archive Network. So really when you're, let me do something real quick. So really when you're accessing R on the internet to do your programming, you're just taking advantage of the free libraries they have available from the software. You have a lot of packages with R, as you saw yesterday and this morning with our workshops. And it is the program for many statistical researchers. Now, in summary statistics, which we will talk about today, is just a part of descriptive statistics that summarizes and provides the important information about the sample data. Statisticians commonly try to describe and characterize the observations by finding, which we will see on the next slide, a measure of location, central tendency, and we will discuss the mean. So there we go with the central location, the mean and the median. Many of us have heard about the mean. It's just refers to the average set of values. The median is the middle number sorted from ascending to descending. This all the numbers in a more descriptive data set versus the mean. The median sometimes is used to, how can I say it, show your outliers that doesn't fit inside your data set. Because the outliers sometimes will skew the average of all values. And we will go over also what they call IQR, which is a measurement of how spread out your whole data set is in entirety. It deals with a few quartiles, like the first and the third, which is pretty important because when it spreads out, when your data is spread out, it'll give you the 50% of the data that's in the middle. Then you have the box plots, as I was alluding to earlier, there are valuable comparisons across different categorical variables or identifying outliers either of those, within your data set. So the mean, as I said before, the balancing point of distribution. For example, you have a gravitational center. The mean is the gravitational center of distribution. So if everything's in balance, that gives you the average. This is a good example of how your data might be on a seesaw. Now, central location is the arithmetic average. Traditional measure of location, central location. You will see the X bar, which is X with a line above it, refers to the sample mean. The sum of the values are divided by n, will give you this equation right here. Good example. You're given these 10 individuals with random ages. So if you want to know the mean, all you do is add them up and divide it by 10, which will give you the 290. Then you take the arithmetic, you take the mean itself, X bar 1 divided by n, which is 290 divided by 10 will give you 29. Now the median, this is just going to be a quick review. Some of us have heard about the median. Now for the 10 values listed below, the median would be here. So your median average would be between 27, 28, 27 and a half. And that is mathematically, that is how you find it. The median is very robust, is resistant to outliers. So that's why it's a little more important than, it's better than using the mean. The median is. And as you can see, data set has a mean, this data set has a mean of 1363. Excuse this, there's supposed to be another break right between the 2 and the 1 right here. And the data set has a mean of 27 with a 2743. Now you see how different the means are from the actual median. So it's not affected by the outliers, which is very important when you're doing summary statistics. This again is the explanation of the quartiles. You have quartile 1, quartile 3. 1 is the median of the lower half. 3 is the median of the upper half. You subtract the two together, this will cover the 50% of the distribution. Graphically, we'll show this shortly. I say box plots. Number 3 here is probably the best because it determines any values outside the fences, such as outliers. You also can determine the values inside the fences. So you draw the whisker from quartile 3 to lower quartile 1. And to get quartile 2, you just use one of the equations up here, or previously as I shown. You also have side-by-side box plots. These are just examples of 2 different groups. Say if you have a lot of, I would say, you want to see a relationship, a box plot would be the best idea if you're using like ordinal nominal values. Now in descriptive statistics, it gets more, usually it becomes the mean and the median summary becomes more important when we're designing graphs, particularly in the next slide. This is called the Gaussian graph. Now in this side here, the d sub f is infinite z, df is 9, df is 1. In the next slide, this may make, actually, let me just do it right now. Degrees, df stands for degrees of freedom. And the z is the normal z distributions. So t distributions, say 60 or more degrees of freedom, are nearly, you can't really tell it between the standard normal distribution. Therefore, in large samples, it really doesn't matter how much you use a t procedure or a z procedure. So this really depends on your sample size when dealing with degrees of freedom. Now, the bell shape and the centered at 0. I'm sorry, the bell shape and the curve centered at 0. The broader tails accommodate for the additional uncertainty that comes from estimating standard deviation with your sample size. In particular for statistics, you're going to have what we call null hypothesis significance testing. These are a few questions. The big question is, you're going to see an observed difference between the groups, real versus merely the result of chance. This will all depend on your p-value that you find. Now, you're going to ask what's the p-value. For those that have never taken statistics, this slide explains the two different statistical hypotheses. You have the HO is a null hypothesis. There's no difference between the means of the correlation is 0 in the population. Alternative hypothesis was the HA. Means do differ. Correlation is not 0 in the population, which means the alternate, it'll be the opposite of what your HO is. Now the p-value used to make a rejection decision. Now, if a p-value, usually the significance we do is 0.05. Now, if it's greater, you don't reject. If it's less than 0.05, you do reject the null hypothesis. In some instances, you're going to find you need to figure out the standard error of mean. And there's a lot of graphical techniques that you can figure that out for. This is based on a book we teach in biostatistics. I can actually get, I believe if Dr. Teng has the link to the PDF, he can put it inside the chat. But generally, we're just discussing graphical techniques coming up with the student distributions, one tail analysis, two tail, and of course, ANOVA. The student T distributions. History was introduced by Gosset. And he wrote it under a pseudonym there. And the T distributions are family distributions of family members sharing common characteristics. T family members are identified by degrees of freedom, which is the DF. DF is the sample minus 1. That means the degrees of, you calculate the DF of the n minus 1. Now, these are the equations you use for one sample t-test. The level of significance, the main thing to take away from this is that your hypothesis, the null hypothesis are equal, or the alternate, they're not equal. So this is where you're going to see sort of like a left-handed, left-sided versus right-sided. It's going to get into two-tailed t-tests. But from this slide and onwards, we're just going to understand just some examples really based on the one-sided test. Now, your S here is your sample standard deviation. X bar is the mean minus the original standard deviation divided by the square root of your sample size. Just an example. You want to know the birth rates. People that babies that have sudden infant death syndrome. In the case that is demonstrated with the following birth rates. First, you have to ask yourself some questions. You're given the data, what do you want to do with it? You're going to analyze it, but why are you analyzing it? You need to ask these questions. Is there a difference compared between the average birth rates in the babies that have SIDS? Any prior research done? In this sample, we have 10 SIDS babies determined by their birth rates. You calculate the average, which is X bar, and your deviation is 720. You get all these numbers, but does the data provide significant evidence that SIDS babies have different birth rates than the rest of the population? So, good time to perform a one sample t-test. Your original hypothesis, the mean is 3,300. The null hypothesis, the mean is 3,300 versus the alternate hypothesis, where the mean does not equal 3,300. This is measured in grams, by the way. Forgot to tell you that. T-statistic is calculated. The negative 1.8. Degrees of freedom is 9. Now, usually we have a chart that shows this. You can also find this on the internet. There's many charts available. So your p-value is greater than 0.05. So there's weak evidence against the null hypothesis. So the data is not significant. So we were not able to say that there is a difference in SIDS babies' birth weight versus normal population. And by the way, the SE X bar is the t-value to the standard error. So the smaller the standard error, the mean, the larger the magnitude of the t-value, and therefore the smaller the p-value. One sample test. This is, we're going to be doing shortly when I switch from the presentation to do some examples with R. Paired samples. Each point has one example is matched to a unique point in the other sample. You have pre-test, post-test, crossover trials, match. Again, it may all sound very overwhelming, but I would encourage you to, if you're going to be a biologist, you still need to have some idea of sample data, population data, how to use descriptive statistics, summary statistics. So I won't really read every one of these, but I'll just highlight the pertinent ones for you. As an example of paired samples, doing where the old brand reduces LDL cholesterol and what they call a crossover design. You cross up based on the subject, you cross over from cornflake diet to bran diet, and this will give you the protocol of the experiment. And you have to calculate the difference variable, which is delta, which we will do in the program soon. This is what they call a paired t-test, which you have no mean difference, which means it's also called like a two-sided test. This is the old brand data, test statistic. The t-statistic is 3.043 with the degrees of freedom is 11. P-value when using R was 0.011. So there is a difference of the oat bran and the oat bran and the cornflake. Our programming makes this very easy since you don't have to do any of it by hand. This is the paired t-test, which we'll go over shortly. Collect data in two samples. You have paired samples, independent samples. Paired samples, each data point is matched to a unique data point in the second sample. Independent, they're unrelated. So in the above figure here with the paired measurements, you can see before treatment, cholesterol. It has to be paired with after. After in the bottom, you have the sample, which is treatment and control. But since this is categorical, so you can't really compare from here because you're not comparing two different techniques used to lower the LDL. So this is just giving you data that will help you later on in the study. So two sample t-tests. We'll show that in a minute. In R is the Welsh two sample t-test that you'll see. It'll include the t-statistic, the degrees of freedom, and the p-value. This is all programmed into R. So as I said, just make sure your data analysis is very good, because if your data is bad, you're going to get bad results from these tests. We'll go over that shortly. ANOVA. ANOVA stands for analysis of variance. It determines if the mean of the groups are different. It helps justify if sample results are applicable to populations. So basically, you're taking what you learned from a small sample population and applying it to an entire population. A lot of commercials that have food, like McDonald's and Coca-Cola, it just test a few people and they try to encourage you to buy their product because of their sample data, but the sample data doesn't sometimes really fit the entire population. So that's another way of looking at it. Previously, we had the estimated standard error of mean for t-distribution. For the ANOVA, we include this arrow with the several samples, which means that a majority, well, I would say all your analysis will be from just sample data. So you're trying to derive a conclusion based on the amount of samples you have. Oh yeah, and another thing you should know is you want your sample data as large as possible. It'll give you a better inference of what the population sample might be. Analysis of variance, as I said before, you have one way analysis of variance, which is ANOVA. Statistical hypothesis here. Of course, the mean 1 equals mean 2. Alternate, at least one of these are different. But in a one-way ANOVA, we're using something called an F statistic instead of a T statistic. The F really measures the variability between groups. Now the ANOVA works by dividing the variance in data set to two components, variance between groups and also the mean square. You might also have variance within groups and also the mean square within. These are a lot of definitions I'm going over, but when you get to the start to actually using it, you can derive a conclusion from the data. You also have the mean squared between. And there's also another one I'll discuss shortly, which is the MSW. These are all, it's a breakdown of every variable in the equation, what it means. Again, this is showing you to use the S statistic. To get to the F statistic, mean square between, you have the degrees of freedom. Like I said, the MSW is right here, mean square within. So you have a mean square within the data set. MSW is mean square between the data. So you have two different groups. Here, SSW, DFW. And again, it's just defining what these terms mean. So when we actually move to R, you can actually understand what the program is doing so you can make sense of all of these variables. Now the F statistic is a ratio of NSB over MSW. This is the main point of sorry. Okay, everybody see this okay again? I think I went too fast with my mouse. So F-stat, MSW, MSB, MSW. This will give you the S statistic, and you also have a table for the critical values. This is based on the data between groups, within groups, that's your total. Summary of the ANOVA. This slide will tell you what's the best used for. The significance level is very, very low number. Remember, the p-value is 0.05 and the t-test. And ANOVA, it's almost, let me see, 1, 2, 3, like 3 times less than that. 3-fold less than that. Also, the p-value is very low. So your data needs to show a difference to go against this p-value. And that's the end of this. So if you have any questions, you can let me know. Other than that, we're going to start doing some R programming.
Any questions?